Bismillah ar-Rahman ar-Rahim. So in the previous chapter, we have discussed the digital transmission, where we transfer the digital bits as a digital signal that has a fixed voltage in a duration of time. And we transfer this digital signal as is on the transmission line. And in that case, the transmission line has a low pass effect. So in this chapter, we will cover the analog transmission, where we actually convert the digital bits into analog signal, which is for broadband communication, where the transmission medium has a bandpass effect on the other side. So, so in this case, we convert the digital bits into an analog signal. So we have to do this, and for this we use the three different pillars or three different parameters for any signal, which is the amplitude, the frequency, the amplitude and the frequency, and the phase, or any combination between them. So here we will cover four different techniques for broadband communication to convert the digital bits into different analog signal based on the amplitude, or based on the frequency, or based on the phase. Or the fourth one here is nothing but a combination of it's nothing but a combination between the first method and the third method, which is a combination between the amplitude shift keying and phase shift keying. What is an example, ya shabab, for a broadband communication system, or a transmission medium that has a bandpass effect? What are the examples for this? What are the examples for broadband communication systems? We talked about some examples where we need to use broadband communication systems. أيوة حسين تفضل. Wireless, تمام. Wireless. What else? For the wire, do we have any broadband communication system in wire? ADSL, bravo عليك. Yes. So ADSL is an example of wired communication that uses broadband communication, where we have to send the digital data as an analog signal over the wired medium. تمام. So here we will cover these four different techniques, okay, for communication. طيب. So as I said, these are the four techniques, and the quadrature amplitude modulation is nothing but a combination between the amplitude shift keying and the phase shift keying. So it combines both the amplitude and the phase to provide the broadband transmission. And we will see the motivation for this. For each of these methods, we need to discuss the motivation. Why do we use such a technique? Okay, and what are the characteristics in terms of, again, pros and cons of each of these techniques? So first, the simplest method is what we call binary amplitude shift keying. So unlike, this is يعني in a way same idea like non-return to zero line coding, except that instead of sending the one as a fixed voltage here, we send the one as a fixed frequency sine wave. As we said, we have to convert the digital bits into an analog signal, so that we eliminate the low frequency components here, okay, because the channel or the medium has a bandpass effect. So the 1 is sent as a sine wave with a fixed frequency, and the 0 is sent as a sine wave with 0 frequency, which means 0 voltage. So, of course, the good thing about this, or in terms of pros, this is the simplest method. This is the simplest form of the broadband communication schemes, the binary amplitude shift keying. Sometimes they call it on-off keying. Why? Because it's actually the carrier or the analog signal is just a sine wave, and we just turn it on or off. So when we turn it on, the sine wave replaces the 1 bit. When we turn it off, we call it 0, or it represents the 0 bit. And in that case, the amplitude is the most important thing here. The amplitude, that's why it's called amplitude shift keying. So the amplitude here, or the peak amplitude of the sine wave, okay, represents the digital bit, whether it's 1 or 0. So in terms of bandwidth, as we said in the previous chapter, the bandwidth is actually the n times 1 over r, right? And the bandwidth or the signal rate, it's n times 1 over r. And here we had the case factor, and the case factor here represents the statistical approximation of the digital signal, whether we are using 1 harmonic, 2 harmonics, 3 harmonics, things like that. And we have to find all the different combinations of the digital bits, represent that using the digital signal, or do some approximation using 1 harmonic, 2 harmonics, 3 harmonics, and stuff like that. And then we calculate statistically the case factor. طبعا احنا we don't do this as part of the course. I will give the case factor to you, so you don't have to actually do this experiments. And the case factor is around half, and it ranges from 0 to 1, and it's usually around half. Okay. So this is called the case factor, and it's based on the approximation. Here, because we are converting the signal to an analog, we are converting the digital bits as analog signal, we have a different effect here. We have what we call 1 plus D, and D here is actually a filtering effect. Okay. This filtering effect is based on how actually the filter that you use to estimate or to detect the signal at the receiver side. So what happens is that if we were to draw the frequency spectrum of this amplitude shift keying, so we can try to estimate roughly what would be the frequency spectrum of this. So we see here that we have 0 frequency, right? But with 0 power. So if you have consecutive zeros, for example, you have 0 frequency but with 0 power. So we have some low frequency component but with 0 power. And as we have discussed before, Shabab, so if we have a short transition like this, what would this lead to in terms of frequency components? This sharp change here, very high frequency, right? So it's around the frequency of the sine wave. So we have this, what we call carrier frequency, and actually the signal itself looks like this, right? So we have the highest power, of course, around the carrier frequency, and we have low frequency components, and we have very high frequency components. So that's the same problem that we had in digital communication, right? Except that here, because of using the sine wave, the highest power exists around the carrier frequency. So we cannot transfer a signal like this over a bandpass transmission medium as is. So what happens is that at the sender side, we have to use some kind of filter. This is at the sender side. So that we can approximate these parts and send a clean bandpass signal over the bandpass channel. Okay, so depending on this filter, we calculate the value of D. واضح كده? So D here is called the filtering effect. The filtering effect. So what is the efficiency of the filter at the sender side that we can use in order to send the carrier signal or the composite signal. So that's why here we see that the bandwidth equation is actually 1 plus D times S. 1 plus D times S. And here S is actually N times 1 over R. So what's R here? What's R in this case? R is actually the number of digital bits, or the number of digital symbol, bits per symbol يعني, over the number of signal elements. Number of data elements divided by the number of signal elements. And here, this is one signal element, by the way. Okay, so this is one signal element. It's one symbol. We call it a symbol. So R is actually 1. Okay, so the bandwidth is actually 1 plus D times N. And N is the bit rate. So if I want a bit rate of N, then the bandwidth that I need is 1 plus D times N, where D is the filtering factor or the filtering effect. It happens that D as well ranges from 1 to 0, except that 0 is possible. Okay, so the case factor, we cannot have 0, of course, because if we have 0, then the signal rate will be 0. We cannot have this. But here we have the filtering effect D. It ranges from 0 all the way to 1. So D belongs to 0 or 1 range. So the minimum value for D is 0, right? And at D equals 0, the bandwidth is actually the signal rate, which is in that case N directly. Okay. So so that's easy. So so the minimum bandwidth. So the minimum bandwidth equals to S, where D equals to 0. Okay, and the maximum is so the maximum bandwidth is 2S, where D equal to 1. واضح كده يا شباب؟ So that's the on-off keying. Right. Of course, yes. يعني we not only that, it's not about the filter, because the filter is at the sender side. We can make the filter as wide as we want, because at the transceiver at the sender side, there's no problem. The problem is, what is the bandwidth? What is the physical limitations of your transmission medium? Your transmission medium has certain limitation in terms of the maximum frequency components that it supports. Okay, so we are restricted by this. So in a way, if we increase D, increase the value of D, okay, so we are actually broadening the bandwidth of the transmitted signal. Okay, but the question is, does the transmission medium itself accommodate this wide bandwidth or not? That's the question. So we have to adjust the value of D based on our knowledge about the transmission medium. واضح كده؟ So the filter design at the sender side affects definitely the amount of bandwidth of the composite signal that we send over the transmission medium. Hence, it affects whether the transmission medium can accommodate this bandwidth or will, in fact, deform or will cause some deformation to the signal that's transmitted, because the bandwidth of the signal transmitted is wider than the actual physical limitation of the medium. Yes, Daniel. Yes, the signal rate, yes. Not always, huh? For this case, as we said, the minimum bandwidth is the signal rate, and the maximum bandwidth is double the signal rate based on the value of D. And we said that the value of D is from 0 to 1. Okay? No. You cannot cover infinity. You cannot have a bandpass filter that covers infinity frequency component. You cannot. And I'm saying this is the practical values for D is from 0 to 1. Okay? So in terms of اتفضل سؤال اتفضل. Sure. All right. So in terms of how to implement as a hardware circuit بقى, how to implement the on-off keying or the amplitude shift keying. So what happens is that we take the digital bits, okay, and we use non-return to zero. This is non-return to zero digital signal at the sender side. I did not send it yet. Of course, I will not send the non-return to zero over the medium. And what happens is that I will have a frequency oscillator. This frequency oscillator is nothing but a hardware circuit that has like a crystal object that generates fixed frequency. This hardware circuit generates a sine wave with a fixed frequency equals to the carrier frequency. And all we need to do is just to multiply the sine wave with the non-return to zero digital signal. So if we do this, then at the 1 bit, the sine wave will be on, and at the 0 bit, the sine wave will be off. That's it. So it's very, very simple. So that's what we do for the on-off keying in terms of implementation. And as we said, this is the maximum bandwidth and this is the minimum bandwidth for the case of on-off keying. About here, this sine wave will change its amplitude as the signal travels through the medium. It loses its power very fast. So the receiver will not be able to recognize the ones from the zero efficiently, in which case the probability of error will be high. And of course, we talked here about the simplest case of ASK, where we have only where we represent the one symbol per bit, which means that either we have a sine wave with a peak amplitude, or a sine wave with a peak amplitude of 0, right? So if we want to represent 2 bits, what will happen? So we have to use sine wave, the same sine wave with the same frequency, but with different peak amplitudes. So we're gonna have 4 different peak amplitudes. If we want to represent 3 bits, we will have the same sine wave, but with 8 different amplitudes. So as the number of levels increases, and as you can see, when the signal attenuates through the air, the receiver will be very confused to recognize the different levels of the sine wave, in which case, so a quick example, if we have an available bandwidth of 100 kilohertz, which spans from 200 to 300 kilohertz. So the signal looks like this. So we have 200 kilohertz, and this is 300 kilohertz, okay? And we have a bandwidth like this. What is the carrier frequency here? Of course, it's in the middle. It's always in the middle of that spectrum. So the carrier frequency equals to 250 kilohertz. That's not what the question is asking for. The question is asking for, we have a carrier frequency and the bit rate if we modulated our data by using ASK or on-off keying with D equal 1. So the filtering factor equals to 1. Okay, so the bandwidth itself is 100 kilohertz, and we know that this is equals to 1 plus d, and d here is 1, okay, times s. S here is n times r, and r here is 1. So n equals to 100 kilohertz divided by 2, which is 50 kilohertz. واضح كده يا شباب؟ So which means that the maximum bit rate that I can have with a bandwidth of 100 kilohertz, sorry, 100 kilohertz, yes, using ASK, the maximum bit rate that I can have is actually 50 kilobits per second, sorry. 50 kilobits per second. واضح كده؟ So n is the bandwidth over 2. Okay, واضح? Any question in this example يا شباب? Wave that we so in network 1 we have studied two types of communication between 2 points. So if we have 2 points like this, if we have a transmitter and a receiver, okay, so and we have a transmission medium with a specific bandwidth, right? We can have two types of communication. We can either have half duplex communication, and by half duplex I mean that the communication is going into one direction. So we always have one acting as transmitter and the other one acting as a receiver, always. So in that case, I can use the entire bandwidth for the transmission in one direction, and this is what we did for the previous example. However, if I want to have full duplex communication, where we have the communication going into both directions at the same time, at the exact same time. So for half duplex, if you want to use the communication in one direction, you use the entire bandwidth. If you want to use it for the other direction, then you have to do that in a different time. And we call it time division duplex. Okay, if we want to use the communication in both directions at the exact same time without طبعا having any collision, then as we said in network 1, we have to use a different frequency. So we have to divide the bandwidth, okay, for both directions, and this is what we call frequency division duplex. واضح الفرق؟ Okay, any confusion about the difference between these two? So half duplex uses time division duplex. So if I want to use the communication in another direction, then I have to do that in a different time. Where for frequency division duplex, I can use bidirectional communication concurrently only if I can divide the bandwidth into both directions. So the same bandwidth that we talked about, which is the 100 kilohertz, I will have to divide it for the case of full duplex. I will have to divide it into two different frequency ranges. One that's used for one direction, and the other one will have to be used for the other direction. Okay, so in that case, the bandwidth for one direction will be, of course, 50 kilohertz, in which case the n, or the maximum bit rate, okay, for one direction only will have to be a 50 kilohertz divided by 2, which is 25 kilobits per second. Okay, so the bit rate for one direction will be 25 kilobits per second. So this is the case of half duplex, sorry, full duplex. So the previous example implicitly assumes half duplex, where we can use the entire bandwidth for one communication. Clear? Any question about this so far? واضح يا شباب؟ The noise effect or okay طيب So this is for amplitude shift keying. And again, for amplitude shift keying, we have to use the amplitude of the sine wave, the peak amplitude of the sine wave, to represent the 1 and the 0. Type, what is the disadvantage for amplitude shift keying, which really motivates us to use frequency shift keying? Well, the motivation is actually the fact that when a signal travels over a long distance, okay, what is the effect of the channel impairment that happens to that signal? The attenuation. Remember, we talked about attenuation. So the attenuation causes the signal to lose its power as it travels through the line, right? So this is a physical limitation that we cannot do anything about it. So whether you transfer the signal over wire or over wireless, the signal tends to lose its power very fast as it travels through that transmission medium. So this actually confuses the receiver to recognize the ones from the zeros efficiently at the receiver side, right? Because the sine wave, the impairment effect will be drastic on the signal, and the receiver will recover the signal with very high probability of error. If we imagine the effect of the channel impairments on the frequency of the signal, okay, it's much less, much less, because as the signal travels through a long distance transmission line, it loses the energy, but the frequency properties does not change much. Of course, it changes slightly because of the noise effect, but it does not change that much. And that's why all of us, we tend to listen to FM radio, but not AM radio, right? And we know that FM radio has a very good voice quality compared to AM radio. That's because of the fact that the noise effect on FM range is actually much less. So واضح كده الموتيفيشن يا شباب. So that's the main motivation behind using FSK. So for FSK, we represent the 1 and the 0 with a sine wave with the same amplitude. As you can see here, the 1 and the 0, they have sine wave with the same amplitude. However, the sine wave for representing the 1 has high frequency, and the sine wave for representing the 0 has low frequency. So in FSK, we represent the digital bits by having a sine wave with different frequency. So if we look at this signal, if we look at this composite signal, it's nothing but two ASK signals superimposed on each other. صح? Because we can think of this part as an ASK with frequency. Let's say this is frequency F2 and this is frequency F1. Okay? So it's as if we create two ASK signals. One is using F2 and one is using F1, and then we combine both. And that's one idea that we will use to implement binary FSK. So for binary FSK, again, R is equal to 1. We use one symbol to represent one data element. However, because of the fact that we use two ASK signals at different frequencies, we end up with a spectrum that looks like this. So, of course, we have two different symbols at two different frequencies. So it's actually, it generates two different frequency ranges, one at F1 and the other one at F2. And one thing to notice here is that for ASK, what happens is that at the receiver side, we use the amplitude to detect whether it's 1 or 0. So we try to detect the peak amplitude of the sine wave to know whether the bit is actually 1 or 0. Whereas for the binary FSK, what the receiver actually uses to detect the 1 from the 0 is that it has to use some kind of a filter to detect whether you have high power in the range of f1, in which case you have 0, or in the range of f2, in the case of having 1. So this is 0 and this is 1. Okay, so if you have high power in the range of f1, you have 0. If you have high power for the range of f2, you have 1. So that's what the receiver in fact does. Why am I saying this? Because of this idea, we have to create some kind of, here we call it guard band. This is called guard band. So we have to keep this separation between F1 signal and the F2 signal. We have to keep some guard band between the two in order to facilitate the filtering of the ones and the zeros. Okay, so because of this, we have to introduce a parameter in FSK which we call it 2 delta F. 2 delta F. Okay, so what is the bandwidth بقى for the case of FSK? Well, we know that we need to have two symbols. Each one will have a duration of S times 1 plus D, similar to ASK. So we have 1 plus D times S for the 0, 1 plus D times S for the 1. However, we have to transmit both, in which case we need to have at least double the bandwidth. However, because of the separation and the guard band, we have to introduce the parameter 2 delta F. So in fact, the bandwidth, if we look here, so if we look at zoomed in, so we have here, this is a half times 1 plus D times S, and this is half of 1 plus D times S, right? So both of them, they sum up to a 1 plus D times S. And in the middle, you have 2 delta F. So in fact, the bandwidth becomes, in general, 1 plus D times S plus 2 delta F. The 2 delta F tries to separate the two symbols from each other using some guard band. Type. What is the minimum value? So 2 delta F, what is the minimum value for 2 delta F? What is the minimum value for the guard band? The minimum value for the guard band is when the guard band in fact is zero. معناها the two symbols are right next to each other. So this happens when 2 delta F equals to a the two halves should not overlap. That's right. So 2 delta F here, 2 delta F. When these two they are right next to each other. When these two right next to each other, when these two, no. When these two here, they are next to each other, what is the frequency range between the two symbols? Between F1 and F2. F2 minus F1, yes, F2 minus F1 is 2 delta F. Okay, what I'm saying is that F2 minus F1, what is the minimum value for the difference between F2 and F1? Again, so let me just zoom in very, very big. All right, so that you can see it clearly. What is so this is 2 delta F. 2 delta F is the difference between the two center frequencies. Right, so half the bandwidth for this symbol plus half the bandwidth for this symbol. So if you combine both, then it gives you 2 delta F equals to, huh? Hmm? Not B. Yes, they are the same. Now we're not assuming they are the same. They are the same. Yes, yes. What is B? B is the total bandwidth. Yeah. Yeah. So the minimum 2 delta F is in fact 1 plus D times S, right? Because when the two symbols are right next to each other, you have half times 1 plus D times S and half times 1 plus D times S. So when you combine both, then it becomes 1 plus D times S. واضح؟ Clear? Not clear? Yeah, go ahead. Go. يعني let's go dig in again. So here, this part is a, what is the distance? What is the duration of this part? Hmm? Half times 1 plus D times S, right? Because this duration, this full duration is 1 plus D times S. صح? So this is half, right? And this is also half. If we assume that this guard band is 0, right? So this means that we combine both. If we combine both, it becomes a 2 times half times 1 plus D times S, which is 1 plus D times S, right? So in that case, the guard band in the middle will be 0, will not be there, okay? So in that case, the minimum 2 delta F is 1 plus D times S, right? There's no maximum. There's no maximum, by the way. We don't have maximum. So you can separate the two symbols as much as you want, okay? So there's no maximum 2 delta F. There's minimum 2 delta F, of course, which is 1 plus D times S. So which means that the the minimum bandwidth, okay, the minimum bandwidth for FSK or binary FSK equals to 2 times 1 plus D times S, right? Because the 2 delta F here is 1 plus D times S, okay? So this is the minimum bandwidth for FSK, which is double, ASK. So the bandwidth for FSK is at least double ASK. واضح يا شباب؟ So of course, if I want to get the minimum with respect to D, then I put D as 0, in which case it's 2S, right? But this is applicable for FSK and ASK, all right? But in FSK, the bandwidth is at least double the bandwidth for ASK. Any question here? So the 2 delta F is the important parameter that we have to use for the case of FSK. So the same example that we had before. So let's take it from an FSK perspective. So if we assume that again we have a bandwidth of 100 kilohertz, what should be the carrier frequency? The carrier frequency is very simple. The carrier frequency, if it's from 200 to 300 kilohertz, what is the carrier frequency? What is the carrier frequency in that case? 250. Yes, it's the same. It's the same. Yeah, I will let you. Yes, this is a good question. So still, if I have, يعني, do not get confused, by the way. So here, if I have whether ASK or FSK, I have one carrier frequency, which is in the middle of the bandwidth. What happens is that for FSK, this bandwidth will be divided into two symbols, right? So each symbol will have, this is F1 and this is F2, right? So F1 and F2 are the frequencies for the different symbols, but still the composite signal has one carrier frequency which is always in the middle of the bandwidth. واضح كده؟ Clear؟ اتفضل. Right. Right. Yes, that's what happens. At the sender side, we have to send a composite signal which has ones and zeros, right? So the ones will be around F2 and the zeros will be around F1, right? But there is always one carrier frequency which is always in the middle of that bandwidth. Always. Okay? So if you want to calculate the carrier frequency, it's always in the middle of the bandwidth. And then here you have 50 kilohertz. And of course here you have 50 kilohertz, right? So what is F1? So this is 250 kilohertz. If you want, of course, the question does not ask for this. But if you want to calculate F1 and F2, then you know that F1 is in the middle of this 50K. So F1 is this is a 25 kilohertz, right? So the F1 is 225 kilohertz, right? And this one is a 275 kilohertz. Of course, the question does not ask for this, but يعني, we can calculate it يعني, if we want. Okay, but the carrier frequency is one for the entire composite signal for FSK. Okay, so the same 100 kilohertz now will be divided into two symbols, and assuming that the 2 delta F here the question says we choose 2 delta F to be 50 kilohertz. Okay, in fact this is the minimum 2 delta F, right? Because 1 plus D times S is 1 plus 1. D is equal to 1, right? This is D, okay, times S, which is N, okay? So this is 1 plus D times S, okay? So if we, so in that case, if we assume that the 2 delta F is 50 kilohertz, if we calculate N is actually 25 kilohertz. So it happens that the 1 plus D times N is actually the 2 delta F. Assuming that we don't know and we just want to calculate N, then we say that the bandwidth equals to 1 plus D times S plus 2 delta F, and 2 delta F is 50 kilohertz. I can change this question in the exam slightly, and tell you what is the maximum bit rate. And I don't have to give you 2 delta F in that case. Okay, so if I change this question slightly, and you know that the equation, it's 1 plus D times S plus 2 delta F. And this is in fact N times 1 over R, and R is 1, right? So what is the maximum value for N? The maximum value for N is when 2 delta F is maximum or minimum? when the guard band is 0, but we don't have 2 delta F 0, huh? When the when 2 delta F is minimum, and we know that 2 delta F is minimum is 1 plus D times S. So the maximum N is when we have 2 times 1 plus D times N maximum. Okay? So in that case, this is 1, all right? So maximum N is actually the bandwidth divided by 4, because the D here is 1, so 2 times 2 is 4. So this is actually 225 kilobits per second. Okay? Which happens to be also when the 2 delta F is 50 kilohertz. Okay? So either I give you 2 delta F directly, or I give you the just a keyword from which you can calculate the value. What if I tell you what is the minimum bandwidth for a specific bit rate? Then also that's when 2 delta F is minimum, right? If I give you bandwidth and I tell you what is the maximum bit rate, then that's when 2 delta F is minimum. Do you have a question, Daniel? اتفضل. Because the signal rate is actually N times 1 over R. R is 1, yes. R is 1, right? طيب. Okay. I think this will take a little bit of time. All right, so we can squeeze it in, I guess. So what is the implementation for the FSK or binary FSK? So the implementation here is that, as I said, we can say, let's just use 2 ASK and superimpose it on each other. Okay, so we use 2 different ASK signals, one at F1 and another one at F2, and then we combine it together. So in that case, what happens is that really what we do is that we can just create a digital signal that looks like this. A low amplitude means 0, a high amplitude means 1. And then we feed that to a voltage comparator, or just a circuit that detects whether it's high voltage or low voltage. If it's high voltage, this is the branch for 1. If it's low voltage, this is the branch for 0. And for the branch of 1, what we do is that we have, again, an oscillator with frequency F2, and then we take this signal with the high amplitude, and then we multiply it by F2, and then we create the signal, and then we do the same for 0 at F1. We multiply, and then we create, and then we take these 2 signals, and then we create the composite signal for FSK. We could do that. In practice, we don't do this. Why? This will generate a signal that looks like this. So for 1, it will be very high frequency, like this. For 0, it will be a low frequency that looks like this. Type. What is the problem here? The problem here is here. So there is some discontinuation. This discontinuation, which is generated from this circuit, we call it non-coherent FSK. Non-coherent FSK creates this discontinuation. And what is the problem with this? حد فاكر ايه البروبلم with this? If we have discontinuation like this, what cause does this have in terms of frequency components? يعني very high frequency components, or infinite frequency components, right? So this will lead to very high frequency components, and that's bad, right? So what we want to do is to create a coherent FSK. Coherent FSK creates some kind of avoids this discontinuation. So if you look here, you find that you have continuation between the ones and zeros. So the signal itself looks continuous. It looks very continuous and smooth. So in that case, you do not have this discontinuations, in which case it leads to high signal. And for that, we need a smart, this is a smart circuit which uses the concept of voltage controlled oscillator. So based on the voltage of the signal, I will create a signal with a different frequency such that there is a continuation between each symbol. There is a continuation between the different symbols. And that's what we call coherent FSK. واضح كده؟ So the implementation for FSK is simple. Just feed the number 10 to 0 signal to a voltage controlled oscillator, which generates a signal with a different frequency with a continuation and smoothness that does not have this discontinuation. Hence, the frequency spectrum is more efficient in that case. The coherent FSK has more spectral efficiency compared to the non-coherent FSK. واضح كده؟ So in practice, that's what we do. We create the composite signal for FSK using coherent FSK using the voltage controlled oscillator. واضح كده؟ There is no what? No, we could introduce the filter here, by the way, Daniel. We could introduce the filter here, right? To filter out the high frequency components. We could do that. But this will lead to also less efficiency because of the approximation. So the voltage controlled oscillator is actually a smart circuit that tries to create that continuation, that smoothness in the FSK signal in such a way that it doesn't actually need any filter in the output of this circuit. Or in other words, you can assume that this filter already is embedded inside the voltage controlled oscillator. Okay, so the voltage controlled oscillator will take care of all the filtering, all the approximation in such a way that creates a continuous signal despite the frequency change between the ones and zeros. Okay, so it avoids completely the discontinuations. All right, using some filtering techniques, using smart techniques, it's much more complicated, by the way. Voltage controlled oscillator is a very complicated circuit. We don't have to get to the details of this. All right.